Today we are going to discuss about the design of RCC slab. So in that first we have to discuss about what is slab. Slab means nothing but it is a structural element whose lateral force, lateral dimensions, that is nothing, the thickness of the slab is considerably smaller than the linear dimensions, which are nothing but length and breadth. So and it is subjected to flexural moments. So what are the uses of slabs? So they are frequently used for floors, roofs in a buildings, as well as decks in the bridges, and the top and bottom slabs are for tanks, water tanks like that, and for staircases, etc. And so many uses are there. Now coming to the types of slabs. So in the types of slabs, based on the support conditions, the slab is divided into three types. First one is simply supported, which is nothing but the supports are on both sides. Now coming to the cantilever slab, which is the support is only up to one end and the other end is free end. This is called as cantilever slab. And the next one is continuous slab, which is more than one span. It is called as continuous slab. Okay. Now next coming to the another type of slabs, which is depends upon the aspect ratio, which is nothing but L by D ratio. So in that there are two types of slabs. One is one-way slab and the second is two-way slab. So coming to which one is called as one-way slab is nothing but if the L is greater than 2 into D, it is called as one-way slab. If L is less than or equal to 2 into D, it is called as two-way slab. Okay. So now the main distinguish between one-way slab and two-way slab. So in the one-way slab, the loads are carried along only in one direction. It is in this direction. So the main reinforcement with cranked bars is provided in this direction only. These rods are only distribution bars. Now coming to the two-way slabs, loads are carried along with both directions. So the bending will be this direction and as well as in this direction also. So the cranked bars are provided in both the directions. Now coming to the example, how to design a one-way slab. Here we are going to discuss about the designing of a slab, which is a office slab having the clear span dimensions of 3.5 into 8 meters with 200 mm thickness wall around the office room. The live load on the slab is given as 4 kN per meter square and adopt M20 grade concrete and Fe415 steel is adopted for this example. Coming to that, with the given data, I have written as the length of the slab Ly is equal to 8 meters, which is nothing but 8000 mm, and the width of the slab in another direction Lx is denoted by 3.5 meters, which is known as 3500 mm, and the support which at all the four edges is 200 mm thickness. The given live load and FCK, because it is M20 grade concrete means, so the FCK is equal to 20 Newton per mm square, and for Fe415 steel, the Fy value is equal to 415 Newton per mm square. So now coming to whether the slab is one way or two way, how we will decide. Ly by Lx, as we discussed in the earlier. So 8000 by 3500, which is nothing but 2.2, which is greater than 2. So hence the slab should be designed for one-way slab. Okay. Now coming to the steps, there are 6 to 7 steps. Now coming to the step 1. So first one, we have to calculate the thickness of the slab or depth of the slab. So which is taken from the IS 456 2000 clause number 24.1. So in that, the assumed L by D ratio is equal to 25. So I have assumed as 25. So D is equal to Lx by 25, which is nothing but 3500 by 25. I got as 140 mm. So now coming to the clear cover. So for each and every RCC structure, we have to provide cover. So the clear cover is taken from the IS 456 2000 table number 16A. So the cover for this slab will be 20 mm. So use 10 mm HYSD bars. So the effective cover will be 20 plus 10 by 2. So clear cover means from the bottom of the rod to the outer surface of the concrete. Whereas the effective cover means from the center of the dia of the bar to the edge of the concrete. So in that, the effective cover is equal to 20 plus 10 by 2. I got the effective cover as 25 mm. Hence the overall depth of slab will be equal to the effective depth plus effective cover. Here we got the effective depth as 140 and 140 plus 25 I got as 165 mm. Now coming to the step 2, which is nothing but the effective span. So as in the problem, it has given as the clear dimensions. So now we have to calculate the effective span. So it is also taken from the IS 456 2000 clause number 22.2. The effective cover is given in the effective span is given in two formulas, which is nothing but L effective is equal to center to center of supports, and L effective is equal to L clear plus D. So with this I have calculated as the effective cover as the 3700 and 3640. We have to take whichever is less, hence the effective cover will be, effective length will be 3640 mm. Now coming to step 3. Now which is nothing but the computation of loads. So the dead load, which is nothing but the self weight, is nothing but unit weight of concrete into L into D. So I have written the values, I have substituted the values with this formula. I got the dead load as 4.125 kilonewton per meter square, and the live load given in the problem is 4 kilonewton per meter square. Now coming to floor finish, which is nothing but tiles or flooring or whatever it may be, it has taken as 1 kilonewton per meter square. So coming to total load, which is nothing but the dead load plus live load plus floor finish, I got as 9.125. So the factored load, which is nothing but the total load is multiplied with the factor of safety. Factor of safety for concrete is 1.5. 1.5 into the total load, I got as total load as 13.69 kilonewton per meter square. So next is step 4, which is nothing but after calculating the loads, we have to immediately calculate the shear force and bending moment. So coming to the calculation of shear force and bending moment for a simply supported beam, which is nothing but WL square by 8. I have substituted the values and I got the bending moment as 22.67 into 10 to the power of 6 Newton mm. Now coming to shear force. Shear force is nothing but WL by 2. Here also I have substituted the values and I got the shear force as 24.92 into 10 to the power of 3 newtons. So now coming to, we have to calculate whether the section is under reinforced or over reinforced. For that the formula is mu. If the mu is less than mu limit, then the section is known as under reinforced. For that we have calculated the mu limit for the formula Q into BD square. I have substituted the values for those and I got the mu is less than mu limit, hence we have to design the section as a under reinforced section. So now coming to the step 5, which is nothing but the flexural reinforcement. So here it is a formula, mu is equal to 0.87 Fy into AST into D into 1 minus AST by BD into Fy by FCK. So here I got the bend, I have substituted the bending moment value and the Fy as 415. AST we have to calculate, and for the D 140, and here also AST is unknown, I have kept it as AST, and B is equal to 1000 and D is equal to 140. Fy is equal to 415 and FCK is equal to 20. I have substituted all the values. I got two values for AST, 6000 change, and another AST is 483. So we have to take the least, hence the AST is equal to 483 mm square. By solving this equation, I got the AST here. So from the IS 456, there is a minimum reinforcement should be provided for slab. There is a clause 26.5.2.1 in that AST minimum is equal to 0.12% of gross cross sectional area. So we have to check whether the AST is in limit or not. So for that I have substituted the values and I got as 198. So which is less than whatever the AST I have provided. So AST minimum is less than AST required. So it is okay. So with this value I have assumed the bars as 10 mm dia bars as a main reinforcement. Now I want to calculate the spacing. For spacing there is a formula 1000 into AST of each bar by AST required. So area of, now I have to calculate the area of each bar, which is nothing but circular, pi by 4 into d square. So I have substituted the values. D means nothing but the dia of the bar here. So I have substituted the value and I got the spacing as 162.2 and I have round 162.6 and I have rounded as 160 mm. So this is the spacing for main reinforcement. So with that we have to check the spacing as per IS 456 clause number 26.3.3 and 26.3.2. Here it has given us for maximum spacing as well as for minimum spacing also. So for maximum spacing it is nothing but 300 mm and the another formula is 3 into D. So take whichever is less. Next, for maximum spacing 300 mm. 300 mm. So minimum spacing of the dia of the bar into maximum size of course aggregate plus 5. So maximum size of course aggregate is 20 plus 5, I got as 25. Take whichever is less. Hence minimum spacing is equal to 25. Here we should satisfy the clause as minimum spacing should be less than spacing required and it should be less than the maximum spacing. So, I got the value as satisfied, hence it is okay. Now, I have written the conclusion as provide 10 mm dia HYSD bars at the rate of 160 mm center to center parallel to the shorter span as main reinforcement at the bottom of the slab, and alternate bars are bent up at the supports. Now coming to the distribution reinforcement. The next step 6 is nothing but the design of distribution reinforcement. From IS 456 clause number 26.5.2.1, the AST is equal to 0.12% of gross cross-sectional area for FE 415, and for mild steel it is nothing but 0.15% of gross cross-sectional area. So I have substituted the values and I got the AST as 198 mm square. So for distribution we can go for 8 mm, it is not required to go for 10 mm. So I have chosen as 8 mm dia bars as the distribution reinforcement. So the spacing formula is equal to 1000 into AST of each bar divided by AST required. So AST of each bar is calculated by substituting the value pi by 4 into dia square. I have got as 50.24 mm square. So with that I got the spacing as 250 mm. So again from IS 456 clause number 26.3.3 B, I have got the maximum spacing formula as 450 mm center to center and 5 into D. So take whichever is less. I got the lesser value as 450 mm. The maximum whatever the spacing we have got 250 is less than the maximum spacing, hence okay. So with this I have written the conclusion for distribution bars also as provide 8 mm dia HYSD bars at the rate of 250 mm center to center parallel to the longer span as distribution reinforcement. Now coming to the check for deflection. As we all know, the formula is L by D maximum is equal to L by D basic into KT into KC. So from IS 456 I have taken the values of KT and KC. For that Fs is equal to 0.58 F by AST required by AST provided. So the AST provided is equal to 1000 into AST of each bar divided by spacing. I got the AST provided as 490.6 mm square. So with this I have substituted in this formula. Fs is equal to 0.58 into 415 into 483 by 490.6. So I got Fs as 240 Newton per mm square, and the percentage of reinforcement is equal to 100 AST into BD. So with this I got the percentage of steel also. From the IS 456 figures 4 and 5 I have taken the value KT as 1.4 and KC as 1.1. So the values has been substituted in this formula. L by D basic is equal to 20 into 1.4 into 1.5, I got as 28. So L by D maximum should be greater than L by D provided what I have taken in the first step. So 28 is greater than 25, hence the section is safe against deflection. So now coming to the last step, which is nothing but the reinforcement details. So whatever the design I got, the main reinforcement as 10 mm dia HYSD bars at the rate of 160 mm spacing, and the distribution bars 8 mm at the rate of 250 mm center to center spacing. So this is the top view, and this is the cross sectional area along x axis, and this is the cross sectional area along y axis. So with this the design of reinforcement of slab is completed. Thank you.